so this is the skeleton, like I say, for the whole course. So some of this might look quite familiar, hopefully. So this is a normal formula interface like you'd use in the LM function or the GLM function. So we're going to be using a column called time as our response variable, and we're going to use all the other columns in the data frame as our covariates. And our data set is this object called melanoma. A core thing we'll be doing throughout all this work is holding out some data sets. So we'll train on some data set or fit the model to some data and then test how well the predictions do on a held out data set. So in this line, we're saying the way we want to do that is leave group out cross validation. So we're just going to pull out, we're going to keep 75% of the data for training and pull out 25% of the data for testing. We're just going to do that once. This is just we want to save all the predictions we make so that we can make scatter plots, basically. Then going back down to this second function again, we define which model we want to use. So we might have all heard of neural networks, random forests, blah, blah, blah. In this course, as our kind of example, we're going to be using this R-part2. Set up how we fine tune that model. I'll go into detail of what this really means, but so some parameters you can't fit directly from data. How do we want to sort of choose those? A definition of what counts as good. So what types of predictions count as good and what count as bad. There's different ways you can define that. And here we're using the mean absolute error. So we're just going to take I'll go into more detail, but it's just sort of the prediction minus the real value, take the absolute value of that and take the mean over the full sort of holdout data set. So like I say, this is the real kind of a skeleton for what we're going to be doing. This is kind of a full machine learning analysis, really, if we want it to be. It's a small one, but it's a full one. And so really most of the course will just be filling all the kind of understanding to what every part of this is. So we're going to be using a data set called melanoma from the package boot. So from this point, if you could go to your scripts and start following through, you can load the data, have a look at the data. You'll see there's one column called time, which is what we'll be using as our response variable. That is that will be the time until death after surgery. So I think these patients had a tumor and they had it removed, and then we were measuring how long they survived afterwards. Most of the other columns are various measurements of either the patient or of the tumor that might be predictive for how long they survive after the surgery. So thickness, I think, is the thickness of the wall of the tumor or something. I'm not a cancer biologist at all. I don't know what most of this stuff means, but that's fine. There's one column called year, which is the year that they had their surgery, and then in the study, the patients were followed up until a certain time, and then after that, the study stopped. So there's right censoring, which we're largely ignoring in this workshop, but Penn will go into it in more detail tomorrow. So please forgive the kind of statistical ignorance of me just ignoring this mostly. But because this year column shows when they had their surgery, it ends up being very, very predictive of the time they survive. So we're just going to remove it. It kind of makes various things in the analysis kind of flow a bit better. Then we've got this function that gives you a nice visual summary of the data. And I think in the script as well, there's just a histogram of the time. So I think it's days survival or something, and you can sort of see it's a relatively sensible spread. It's nothing too bonkers. I think that looks like most people. Great. Okay, so then at that point, we can go straight in and run an analysis. So we run this train control function from caret that sets up our data holdout and a few other things. And then we run this train function which fits, we'll go into detail more later, but it does actually quite a lot. It fits a number of models and then makes the predictions from those models to test against the holdout data. And so if you run this train function and then type 1 M1 into the console, or type print M1 or whatever you want to do, you'll get some output like this. So yeah, I'm aware that this is very shallow to start with. We're just going to kind of skim right over the full analysis, and then we'll go into detail later, and I hope that's okay for everyone. So when you print that object, it tells you the model you use. So we used R part 2, but that's kind of a code for using a caret model, which is a decision tree. Again, we'll go into more detail of what those are, but it's just the type of model we're using. Bit of a summary of the data set. We had 205 samples and 5 covariates. We didn't do any pre-processing. The way the form for our holdout data was to, we just did one replication of using 75% of the data for the training data. So in that kind of split data set, we were left with 156 data points for model training or model fitting. So then this is the tuning parameters that, again, we'll go into more detail, but we've got a parameter called max depth that can't be fitted directly to the data. So instead, we tried a number of different values for this parameter, 1, 2, and 3. And then we got the performance sort of metric for each of those against the held out data. So the mean absolute error when max depth was 1 was 697 days. So on average, we were wrong by 697 days, but that can be improved a little bit depending on how this tuning parameter is set. We used MAE to select the optimal model, and the best model was this max depth of 3. So, what is machine learning? It's modeling where the focus is prediction, and we're not aiming to get good predictions by building sort of mechanistic models that really sort of are an accurate sort of summary or description of the world. We're doing very data-based, data-driven models that just do good prediction, and that's all they're made to do. And sort of relatedly, we're therefore not trying very hard to get nice inference of real-world parameters. Often these models have parameters that are difficult to interpret or impossible to interpret, or they have just thousands or millions of parameters. And often the uncertainty on the parameters is not nicely characterized either. So we're not doing careful statistics for 1 or 2 parameters of interest. We're trying to do prediction, and that is the focus. So this is an analytical aim rather than, it's not like a set of models. It's not this model is machine learning and this isn't, or anything like that. Or it's not like you need, if you've got more than 1,000 data points, it counts as machine learning, and if you've got less, it's statistics. If your aim is prediction, and if the way you're doing that is with flexible data-driven models, then in my mind that counts as machine learning. And so in that sort of context, things like linear regression that we all know from statistics can be machine learning if that's what you're using it for. So this comes up quite a lot. If you've got an awful lot of covariates, you might be running simply linear regression on your data, but all you care about is prediction. That is machine learning. And so related to this is a sense that actually a lot of the topics we'll talk about today, a lot of the concepts can be transferred back to your kind of more classical statistical work as well. I won't kind of highlight those, I guess, but especially if you use any sort of flexible models in statistics, so if you use GANs or Gaussian processes or the spatial random fields or Kriging are all types of Gaussian processes, a lot of the concepts we'll talk about apply directly to those types of models, even though they're quite statistical, and even though the analytical aim there might be much more about interpreting a small number of important parameters. And then, yeah, just some of the models we've probably heard about a bit more include like neural networks, decision trees, and random forests. So while linear regression can be machine learning, often it's not like the best method or something. So, you know, often we'll be using other methods. So there's three main tasks in machine learning. There's what's called supervised learning. That's where we have some covariates, one or more covariates, and response data. And we're trying to find relationships between those covariates and the response data. And so really, I think most biological models that we encounter in our biology work or in papers or in our biology statistical lectures, for example, come under supervised learning, really. So linear models, generalized linear models, t-tests, ANOVAs, all these types of models, they have one or more covariates and a response variable. So they come under this umbrella of supervised learning. Reinforcement learning is what you hear about a lot. It's kind of some of the sexy stuff in the media turns out to be reinforcement learning. If it's robotics or teaching a computer to play computer games or, you know, to play chess or something, this will typically be reinforcement learning. And the salient factor of reinforcement learning is that the computer or the robot data. So it says, I'm going to try this new idea. I'm going to try this kind of, here's my new model for how to play chess. I will try that by playing against another chess player or another chess engine, and I'll see how well it does. And so the task is really to find which things you should ask and which things you could try, rather than having like a fixed set of data in the first place. As far as that comes up in biology, very rarely, as far as I'm aware. I've seen maybe one application of it in biology. So we won't talk about it anymore, but it's worth knowing that it exists. And unsupervised learning, we often call clustering. It's where you've got some covariates, but no response data, and you just want to sort of summarize the relationships between your data without any reference to a kind of a most important response data. So this comes up in biology sometimes, and certainly things like building phylogenetic trees could count as unsupervised learning. So this comes up sometimes, but by far and away the sort of task we most often see in biology is the supervised learning. So supervised learning will be the focus of the workshop today. We won't talk about reinforcement learning at all or unsupervised learning anymore, even though unsupervised learning does come up in biology fairly often. Within supervised learning, there's two broad things we might be doing, which just depends on the form of the response data. So if our response data is a categorical variable, like is it a picture of a cat or not a picture of a cat, then we call this classification. You can have two labels, sort of two classes, or you can have many classes. So have some pictures, is it a cat or is it not a cat? Or you can have some pictures and is it a cat, is it a dog, or is it neither? So that would be called like two label classification or multi-label classification. And then alternatively, we can have what in machine learning we call regression, which is where the response variable is a continuous number. So in machine learning, regression refers to any type of model that does that relates covariates to a continuous variable. In sort of biology and statistics, we might often refer to regression being sort of a quite a small subset of these models being like kind of, we might talk about only linear regression being regression, but in machine learning, anything where we have covariates and a continuous response variable is called regression.